Hi everybody. I was looking around for some videos on logarithms and properties and everything, and there are a lot of videos online on YouTube about logarithms and properties and all kinds of different things. But I think the most efficient way for us to kind of get what I want you to get really is to just kind of go through the notes that we've done. So this is a little video rundown of the notes we've taken over the last couple of days about logs and log functions and properties of logs, etc. Okay, so let's get going. Log expression, as you've been dealing with a lot lately, it has this kind of odd thing here. Here's the log. This is the snail thing that we drew after a while. But log base b of x equals y is the same thing as saying b to the y equals x. The base of the logarithm is the base of an x is a base for an exponent that is y. And this base to that exponent gives you x. Okay? We call that the snail. Sitting on a log there, a happy little snail. Okay? And there's a couple of restrictions on this expression, log base b of x equals y. It's assumed that b is a positive number not equal to 1. And that's mostly for convenience. But we almost always restrict b to being a positive number not equal to 1. Any fraction greater than 0 except 1, or any number. X, the argument of the log expression, is also always positive. The argument. What we call that thing there in the, for the logarithm. That always has to be greater than 0. If there is no written base number for b there, then the base is assumed to be 10. And this is because how logarithms first started out being used. It was always base 10. And so that just kind of became the usual thing. Here's a few examples of evaluating logarithms. So 3 to the third, so log base 3 of 27 equals 3 because 3 to the third equals 27. We've seen these before. Log base 4 of 2 equals 1/2 because 4 to the 1/2 power equals 2. That's like saying the square root. So when a logarithm equals 1/2, that's a square root going on in there, okay? The log base 6 of 1/6 equals -1 because 6 to the negative first equals 1/6. Here's another one with a negative x result here. So the base to a negative exponent gives you a fraction. Okay, so when you have log of a fraction, you might think, oh, negative exponent. Okay? All right, so let's move on to the idea about log functions and the basics on log functions. All right, so we talked today in class about what a log function looks like. Again, log functions are the inverse of an exponential function. An exponential function reflected across the line, y equals x. So see the video about inverses, for more reminders of that. Will give you this log function right here. The horizontal asymptote of the exponential function reflects to being a vertical asymptote for the log function. So they're really the same curve, except just reflected across this line y equals x. The domain and range of the exponential function interchange to be the domain and range of the log function. So notice that the domain here is all real numbers. Well, that's the range of the log function. And the range of the exponential function is the domain of the log function, okay? So all that switching or interchanging between x and y values, between domain and range, and across this line here, y equals x, all that stuff is very important conceptual basis for the log function, okay? Log functions can be transformed just like any other function. If the argument is x minus 3, that's shifting it to the right 3 units. We had something just like that in the PDN for today. Adding a number shifts the graph up or down. In this case, adding a negative number shifts it down 5 units, but adding a positive number would shift it up. And okay, so all those transformations that you apply to other functions work exactly the same way for log functions. So you just kind of have to make sure you get that shape kind of implanted in your memory there. Now, another important thing about a log is that a log function, since it is the inverse of an exponential function, that means that taking the log of a number is like a mathematical operation that happens to be the inverse operation of raising to a power, or exponentiating is actually what that's called. So taking the log is the inverse of raising to a power. This means that if you have an exponential equation, you can undo that exponentiation by taking the log. All right, so we'll get to that a little bit later. But that was the basics on log functions there. All right, and then the next thing that we talked about was some basic properties, and we will get into solving some equations here in this part of the discussion. So basic properties of logarithms, and these come out of your basic understanding of that snail idea that the base to this power equals that number right there. These two things are just kind of naturally and hopefully kind of obvious, because if you have a log equal to 0, that must be, the argument has to be 1. You know, if you just have log of 1, well, it doesn't matter what that base is, that's going to equal 0. And if you have a log equaling 0, then that means the argument has to be 1. And that goes for every single base, because any number to the 0 power equals 1. Also, if the base and the argument number are the same, well, then that just means that you've got that logarithm equals 1, because b to the first equals b. Any number to the first power equals itself. And if you extend that a little bit, you get this very interesting and useful thing. It's also kind of obvious, but it's not so obvious when you just look at it by itself. When the base number and the argument number are the same, and that argument number is raised to a power, in other words, you're taking the log base b of b to some number, well, that just equals that number. The exponent there would be the same, because for this, again, the same reason there, b to the x equals b to the x. Well, duh, of course it does. So it seems really obvious when you see it that way, but it is confusing just to kind of look at an expression like that and think of simplifying it. But take heart, it just equals the exponent. This last one here, what I call some of these basic things, this is a similar idea to this one right here. When the base is raised to the logarithm of the same base, it equals this argument here. And I don't want to get too caught up in this, because this is it's a little bit tricky to work your way through this. So it's one of these things where we don't necessarily have to understand it, but you just do have to get used to it and be able to recognize it. Won't happen too often though. One of the most important properties of logarithms is called the power rule for logarithms, or power property. And that says that when you're taking the log of a number raised to a power, that exponent can be written as a coefficient of the logarithm. So log of x to the n equals n times log of x. And this is really helpful in solving exponential equations, okay? Such as a really simple one, 2 to the x equals 10. That's an exponential equation because the exponent is the unknown variable in the equation. If you take the log of both sides, and we've done this a bunch in class, so I don't have to go through this too slowly, but when you take the log of both sides and then move this x down, you've got x times log 2 equals log of 10. Divide by log of 2 there to isolate the x, and there's your exact value for the value of x, exact expression. It's approximately 3.32193. So that's how you can use that. That's an application of that power rule. A couple of the other rules that we talked about real quickly are the product rule and the quotient rule on the next page. Let me get back to that. Sorry, I'm a little out of order here. When you're solving an exponential equation, it is really important to isolate the exponential part first. Always do that first. You cannot take the log of both sides of the equation until you isolate the exponential part. So really important that you get that straight. Once the exponential part of the equation is isolated, then you take the log of both sides and you can use the power rule to isolate the variable and solve for your unknown. So here's an example of $1,000 in a bank at 3.1% per year. The question is, how long will that $1,000 turn into $2,000? Well, okay, so here's an equation that expresses that relationship. If it's growing by 3.1%, then that means it's 100% plus 3.1%. In other words, 1.031. That's our multiplier. Every year it's going up by 3%. Every year you have that 103.1%. So we express that this way, and there's our exponent of t. 1,000 times that multiplier at some point will equal 2,000, and we're just trying to find that exponent. So isolate the exponential part by dividing by 1,000. Then you get this number all by itself equals 2. Not so bad. Then using our power rule, rewriting it, we get this fraction down here. It's about 22.7 years. We've been through this a few times, so hopefully it was okay to go through that kind of fast. The other property that we talked about is called the product rule, and that says that the log of a product is equal to a sum of logs of the factors of that product, to be precise. In other words, log of a times b is the same thing as log of a plus log of b. And these are two-way equations, of course. If you had a sum of logs, you could simplify it to a log of a product of those two things. So if you started with log of 3 plus log of 5 and had to simplify that, that would be the log of 15. Or if you had the log of 2 times x, you could expand it out to log of 2 plus the log of x. And so on. A couple more examples here for you to gaze at and wonder. If we had log of 3x squared, we could write it this way, but 3x is a product, so I'd split it up like this, log of 3 plus log of x plus log of x. Well, that's 2 log of x right there, so probably the best way to write this, log of 3x squared in expanded form, is log of 3 plus 2 log of x. All right, the other important property involving this rewriting of logs is called the quotient rule. It's kind of the inverse of the product rule. It's saying in words that the log of a quotient, or a fraction, is equal to a difference of logs. And kind of symbolically, we might write it this way: log of a over b is equal to log of a minus the log of b. Please pay very careful attention to how this is, okay? It's the difference of logs, not a log of a difference. It is not log of a minus b or log of a over log of b. Those are different things. Log of a quotient is equal to a difference of logs. Okay, and there's a few examples here for you to look at. Don't think we have to go into too much depth about them. You can pause the video and examine them if you like. Here's one thing you might want to focus on: log of square root of x minus log of x minus 1. A couple of things here. The square root of x could be written as x to the 1/2 power. So this log of a square root could be written as 1/2 times log of x. Another thing to note, log of x minus 1 does not simplify. You can't break this up. Log of a difference or log of x plus 1, or any kind of a sum inside here as the argument, it has to remain intact. You cannot split it up or simplify it anyway. Okay, here's an example kind of combining a couple of things. Log of x plus log of 3 minus log of y. So here's a sum of logs. We could write that as log of 3 times x. And since we've got that, then subtracting log of y, there's our quotient. So we can simplify that as a single log of 3x over y. Okay, that's long enough for this video. Hope that was helpful. Now let's go do some math and be well. Bye.